Assalamu alaikum. Welcome to the next lecture. In this lecture, we'll be discussing about the corona and the laws associated with this. Let us start with the introduction of this topic. Actually, this corona phenomena is the ionization of the air surrounding the power conductor. We know that the free electrons are normally present in the air because of the radioactivity in cosmic rays. They dislodge electrons from the atoms or ions, and these electrons are usually present in the atmosphere. As the potential or the voltage across the conductor is increased, you can see the gradient, that is potential gradient or electric field also increase at the surface of the conductor. Assuming that the spacing between the conductors is large as compared with the diameter of the conductor, this is an assumption while we analyze the corona, and this will be helpful in deriving some derivations. So these free electrons will attain certain velocity depending upon the field strength. If this field strength is very high, you will see that these electrons will collide with the molecules of air, and in case the speed is large, they will dislodge electrons from the molecules, and thereby the number of electrons will increase. So this type of ionization or this process of ionization is cumulative in nature, because when the number of electrons increases because of dislodging of the electrons from the air molecules, they will try to dislodge the other electrons from the air molecules in the atmosphere present. So this is the cumulative process, and it forms ultimately an electron avalanche. This results in ionization of the air surrounding the conductor. So all the air which is surrounding the conductor is ionized. So in case the ratio of the spacing between the conductor to the radius of the conductor is less than 15, flashover may occur between the conductors before the corona phenomena occurs. So flashover occurs, it results in the short circuit between the conductors. So that's why I told you in the beginning that the distance between the conductors should be greater than, very large as compared to the diameter of the conductor. It should be greater than 15. Otherwise, because of this corona phenomena or because of this ionization of the air surrounding the conductor, it results in the breakdown. Usually for our lines, this ratio is far more than this number, and hence flashover can be regarded as impossible. So it means this is very large as compared to this value 15. So in practice, this does not occur, and we have witnessed such thing that this never has happened because of this. Let us see what will summarize all these points in simpler definition. This corona phenomena is therefore defined as a self-sustained electrical discharge in which field-intensified ionization is localized only over a portion of a distance between the electrodes. So it is self-sustained electrical discharge, self-sustained because of the voltage of the conductor, uh, and it is usually localized. It means it is only, it does not go beyond the vicinity of the conductor. It lies only in the vicinity of the conductor. So that's what it is, what is meant by the localized. And it is field intensified ionization. The ionization takes place because of the electric field that is produced by the voltage, and this electric field will dislodge electrons, and these electrons will dislodge the further electrons, and it is a cumulative process leading to the discharge, electric discharge, or we can say electron avalanche. So this is what is meant by the definition of the corona. Now let us first try to uh, derive the potential gradient, and we know the potential gradient is also known as electric field. We'll try to find out its value or its formula for a single phase line. Before going into that, let us say we have a conductor over here. It has a linear charge density of Q, coulomb per meter, and we need to find out the electric field at a point x distant from its center. So we know from the Gauss law that closed integral of E dot ds is equal to Q encircled by the epsilon naught, where Q encircled is the charge encircled by any Gaussian surface. We will select a Gaussian surface of cylindrical nature whose length is L and whose radius is x. and we'll superimpose it on the conductor so that they are coaxially placed within with respect to each other. These are the electric field lines. So at any point they will be radially they'll be pointing radially outwards from this conductor, and at a point x you will see all the electric field lines will be parallel to each other and they will be equal in magnitude. And this is the surface element of this Gaussian surface ds, and we, as you know, that the direction of the surface will always be perpendicular to the surface. So this is the surface, the direction of this ds will be perpendicular to this, and the direction of the ds and the electric field at any point on the surface of this Gaussian surface will be parallel to each other, or they will be in the same direction. That means the angle between electric field and ds will be equal to 0. So let us try to solve this equation. That's closed integral of E dot ds is equal to q encircled by the epsilon naught. And what will be the q encircled? The charge on this conductor is q coulomb per meter. So the total charge encircled by the surface will be charge multiplied by its length, that is L. That is q encircled will be q into L. So opening up this integral will be closed integral of E dot ds cos of theta, while cos of theta is equal to 1, it will be integral of E dot ds. And we know that at every point on the surface of this Gaussian surface, this E is constant, we can take this out. So integral of ds is equal to q into L divided by epsilon naught, where this ds is the surface area of this Gaussian surface, that is the curved surface area of the cylinder, that is 2 pi r into x, where r here is equal to x, that 2 pi x into L. So E into 2 pi x into L is equal to Q L by epsilon naught. This L and L will cancel out. So E is equal to Q divided by 2 pi x epsilon naught volt per meter. This is actually electric field. This electric field is also known as potential gradient, and it is usually denoted by G in almost all the books. So potential gradient is given as Q by 2 pi epsilon naught x volt per meter. So let us consider a single phase transmission line, and let R be the radius of each conductor, and they are placed at a distance of d from each other, and let charge q be on the conductor A and minus q charge be on conductor B. And let us assume that our operating voltage V is operating between between A with respect to B. So the voltage of A with respect to N, we'll consider it to be V by 2, and the voltage of B with respect to N will be equal to minus V by 2. Let us consider a point P which is at a distance of x from the conductor A, where we want to find out the electric field intensity. So if we try to find out, what we usually do, we take a test charge of positive charge, and at this point that will have a repulsive nature from point A and attractive nature from conductor B. So the total electric field in both the cases will be in this direction, that in the direction of B. It will be additive in nature. So this Ex will be equal to then Q by divided by 2 pi epsilon naught x, using this formula Q by 2 pi epsilon naught x, because we are calculating with respect to x, and Q divided by 2 pi epsilon d minus x, because this electric field due to this x, due to this charge, will be at this point d minus x, because the distance from this point to this will be d minus x, and it will be additive in nature because of this positive charge will be attracted towards this B because of A conductor and A because of B conductor. So taking this Q by 2 pi epsilon naught outside will be 1 by x plus 1 divided by d minus x. So the potential difference between the conductors will be the integral of Ex dx from this d minus r, that means from this point to this point. So by changing this, the limits of the integration, this minus will be consumed, so it will be equal to d minus r to r q by 2 pi epsilon naught 1 by x plus 1 by d minus x. So the integration of 1 by x is ln of x, and integration of ln of d minus x will be equal to ln of d minus x, and the internal differentiation of this will be minus 1, that is what that comes over here. So total it will be equal to q by 2 pi epsilon naught when you put the values, these values, it comes out to be 2 times ln of d minus r divided by r. So this 2 and 2 will cancel out. It will be 2 q by this pi epsilon ln of d by r. So where r is very small as compared to the d, so d minus r can be considered to be equal to d. So v is equal to q divided by pi epsilon naught ln of d by r. This is the voltage of A with respect to B as a function of d, r, and q. So now the gradient at any point x from the center of the conductor A is given by again the same equation q by 2 pi epsilon naught 1 by x plus 1 by d minus x. When you solve it, it will be d minus x plus x divided by x into d minus x. X and x will cancel out. It will be d divided by x into d minus x. So from the earlier equation, v is equal to q by pi epsilon naught ln of d by r. So q is equal to v pi epsilon naught divided by ln of r. So I will substitute the value of q over here as v pi epsilon ln of d by r. That's v pi epsilon ln of d by r. That is v pi epsilon ln of d by r into 1 by 2 pi epsilon naught into d divided by x into d minus x. This epsilon pi will cancel out with this. It comes out v divided by 2 ln of d by r into d divided by x into d minus x. This is the electric field at point x. Now I'll replace this v divided by v dash. This v will be replaced by v dash, and rest it will remain as it is. So it will be v dash d x into d minus x into ln of d by r. So v dash d x into d minus x into ln of d by r. Now what is this v dash? This v dash is the line to neutral voltage of the system. Since we have considered this v to be the voltage of A with respect to B, v dash will be line to neutral voltage. That means v by 2 will be equal to v dash in this single phase system. Where v dash is the line to neutral voltage of the system, in case of three phase system, v dash will be equal to VL by root 3, that is line voltage by root 3, where VL is the line voltage. From the expression of the gradient, it is clear that the given transmission system, the gradient increases as x decreases. So you can see from here, as x decreases, gradient increases. So we need to find out where will be the maximum gradient. The maximum gradient will occur when x is equal to r, that is at the surface of the conductor. When we put that, we replace this E by G, and we call it as Gmax. So that is equal to ER, that is the electric field at the surface of the conductor, or Emax, that is equal to V dash D, and we have to replace x by r, that is equal to r d minus r into ln of d by r. And we know that d minus r, d is very large as compared to r. We can consider this d minus r to be equal to d. So this d and this d will cancel out. It comes out to be v dash divided by r ln of d by r. So finally this v dash, that is the voltage of A with respect to the neutral point in case of single phase system, will be equal to r g max ln of d by r. Now coming to the critical disruptive voltage, this is voltage at which the complete disruption of dielectric occurs, or beyond which the corona takes place. So we can say this is the voltage at which the electrical discharge takes place, and in more sophisticated way we can say that this is the voltage at which this corona takes place. If uh, if the system voltage is less than disruptive voltage, corona will not take place. So this disruptive voltage is actually a property of the system, inherent property of the system, and we need to see that whether we will increase the voltage as per this disruptive voltage or not. So ideally we should keep our operating voltage less than disruptive voltage, critical disruptive voltage, so that corona will not take place. This voltage corresponds to the gradient at the surface equal to the breakdown of the strength of the air. So actually this is the voltage where the breakdown of the air takes place around the conductor. So this dielectric is normally denoted by G naught and is equal to the 30 kilovolt per centimeter peak at normal temperature and pressure, that is at 25 degrees centigrade and 76 centimeter of Hg. So in general, this is very important that the normal dielectric strength or breakdown strength of the air is 30 kilovolt per centimeter at NTP. So but it will change as temperature and this pressure will change. At any other temperature and pressure, this G naught dash will be equal to G naught into delta, where delta is the air density correction factor and is given by 3.92 B divided by 273.T. We don't have to go into the derivation of this delta, but in general we can see that this G naught, or we can see this dielectric strength, will depend upon the temperature as well as the pressure, because ultimately the dielectric strength depends upon the availability of the electrons, and when pressure increases, this availability of electrons will increase. If temperature increases, this availability of electrons will decrease. Or in general, we can say this delta or air density correction factor will depend upon the pressure as well as temperature, and that relation is given by this formula, where B is the barometer pressure in centimeter of Hg and T is the temperature in centigrade. Therefore, the critical disruptive voltage is given by, that is, V dash is equal to R G naught delta, because here we have to replace this G naught by G naught into delta ln of d by R. We have actually modified this equation. Now G max will be equal to G naught into delta. One more correction factor we have to introduce, that is, in deriving the above expression, an assumption is made that a conductor is solid and surface is smooth. In that case, it will be quite okay to use this formula. For higher voltages, ACR conductors are used. The cross section of such a conductor is a series of arcs of circles, each of much smaller diameter than the conductor as a whole. So the cross section will be the circles, as we have discussed and done in our classroom. There are different strengths and they does not exactly make circle or smooth surface. There are smaller circles which are connected to each other, combined or placed at each other to make such conductor. The potential gradient for such a conductor will in consequence be greater than for an equivalent smooth conductor. Potential gradient will be greater. When potential gradient will be greater, their critical disruptive voltage will be smaller. So the breakdown voltage for the stranded conductor will be somewhat less than the smooth conductor. Their breakdown voltage will be lesser. The regulator on the surface of the conductor are increased further because of the deposition of the dust, dirt on the surface, and breakdown voltage is further reduced. Again, one more thing is the irregularity. It may not be the regularity of, we can say, hexagonal type of the surface. There may be some irregularity. This also further decreases the breakdown strength, and the deposition of the dirt, or we can say dust, this will also result in the decrease in the breakdown strength. So an average value for the ratio of breakdown voltage for such a conductor, that means which is an irregular conductor, and a smooth conductor lies between 0.85 to unity and is denoted by m0, that is known as irregularity factor. Suitable values of irregularity factor m0 are given by, for polished wire and smooth wire it's equal to 1. So that means we don't have to actually introduce it. For roughened in weather wire, it is value is 0.98 to 0.93. For 7-stranded cable, it is 0.87 to 0.83, and large cables with more than 7 strands, 0.9 approximately. So the final expression for the critical disruptive voltage is given by this, that is, V dash will be equal to R G naught delta m naught ln of d by R, and it will be in kV because this G naught is in kV, and in this derivation this R has to be in centimeters, because this the value of G naught is kilovolt per centimeter. This value should be in centimeters, so that centimeter will cancel out and we will get the final value in kilovolt, and delta m naught and this term is unitless. So here also you have to be very careful. The unit of D and R should be same so that they will be unitless. Usually the D is in meters and R is in centimeters. You have to change D in centimeters or R in meters as per the requirement. So putting the value of G naught, that is 30 kilowatt per centimeter, then V dash will be equal to 30, that is the value of G naught, into R delta m naught ln of d by R. It will be the peak value of the voltage, critical disruptive voltage, and RMS value will be simply divide root 2 to this value. It will be 21.21 into R into delta m naught ln of d by R. This is the critical disruptive voltage value. Now we may have another one, that's critical visual disruptive voltage. Because corona takes place, it may not be visible. Sometimes when this voltage, operating voltage, is much higher than the voltage, it will result in the visual corona. When the voltage applied corresponding corresponds to a critical disruptive voltage. Corona phenomenon starts but is not visible because the charged ions in the air must receive some finite energy to cause further ionization by collision, and when the collision occurs they emit the radiation, and that radiation is in visible range. For a radial field it must reach a gradient of GV, which is definitely greater than the G naught at the surface of the conductor to cause a gradient G naught a finite distance away from the surface of the conductor, which is slightly away from the surface of the conductor. The distance between GV and G naught is called the energy distance, and this, according to Peak, that is a name of a scientist who thoroughly uh, discussed this and thoroughly visualized this and gives us the value of this distance. It is actually R plus 0.30 R for two parallel conductors and R plus 0.30 R for coaxial conductors. From this, it is clear that this GV it is not a constant like G naught, it is a function of size of the conductor, because you can see for two parallel conductors it is value something else, and for coaxial conductors its value something else. Now the empirical formula that is given by P for the critical disruptive voltage or critical disruptive dielectric breakdown, that is GV, that will be equal to G naught into delta into 1 plus 0.3 divided by R root of R into delta. So here when this happens, so V that is critical visual disruptive voltage is GV R into ln of D by this. So finally this comes out to be when irregularity factor, air density correction factor are taken to be considered, it comes out to be G naught MV delta R 1 plus 0.3 divided by R into delta ln of D by R. So when taken into given the value of G naught and when the RMS value is taken simply by dividing root 2, it will be 21.1 MV delta R 1 plus 0.3 by square root of R into delta ln of D by R kilovolt in RMS. The only difference between critical disruptive voltage and critical visual disruptive voltage is only this term. When you multiply the critical disruptive voltage by this term, you will get critical visual disruptive voltage. So here MV is again equal to 0.1, sorry 1.0 for polished wire. It is the irregularity factor and it's equal to 0.93 to 0.98 for roughened conductors and 0.72 for local corona on stand-in conductor. Local corona means which are very close to the vicinity of the conductor. Since the surface of the conductor is irregular, the corona does not start simultaneously on the whole surface, but it takes place at a different points of the conductor which are pointed, and this is known as local corona. As I have told you that the local corona is the corona at this takes place at the points where the surface is more irregular, more pointed. When the surface is more pointed, the radius is very small, and in that case, the potential gradient is very high, and it results in corona. So that's why for this MV is taken to be 0.72 for local corona, and for general or decided corona it is taken to be 0.82, because in that case the irregularity will be lesser as compared to the pointed irregularity. Now let us try to do some numericals, and it will be quite easy to understand. Find a critical disruptive voltage and critical voltage for local and general corona on a three-phase overhead transmission line consisting of three stranded copper conductors spaced 2.5 meter apart at the corners of an equilateral triangle. Air temperature and pressure are this: the conductor irregularity factor and the surface factors. This is conductor diameter, this is irregularity factor, this is the conductor diameter, irregularity factor, this is irregularity factor, and the surface factors. These are two surface factors for local and general uh, corona. Now the critical disruptive voltage is given by, that is V dash. Usually sometimes it is denoted by VD, sometimes it is denoted by V naught. It is given by 21.1. Sometimes it is denoted by VD, sometimes V naught, sometimes VM. 21.1 M delta R ln of D by R. First we'll calculate delta. Delta is equal to 3.92 B divided by 273 plus T. So giving the value of this, it comes out to be 0.9813. So D is equal to 2.5. That's why 250, because it has been converted to uh, centimeters, and this also has been converted to centimeters, because this is 10.5 millimeter. It will be equal to 1.04, 10.4 millimeter, 1.04 millimeter, and its half will be 0.52 centimeters. So it comes out to 56.5 kV. So critical disruptive voltage line to line multiplied by √3, we will get 97.89 kilovolt. So critical visual disruptive voltage 21.1 m delta r into 1 plus 0.3 root of delta r ln of d by r. So m is equal to 0.7 for local corona, m is equal to 0.8 for decided corona or general corona. So calculating square root of r into delta, it comes out to be 0.52 into 0.9813. So here I perhaps forgot to mention that here also r should be in centimeters. I haven't written over here, I don't remember. Yes, where r is the radius and it should be in centimeters in this case. In this case also. Here also it is quite evident that when we multiply r into this kV per centimeter, it should be in centimeters. Here also it should be in centimeters. So that's why we have taken over it in the centimeter. So it comes out to be 0.71433. So putting these values and calculating for local corona, it comes out to be 66.07 kV, and the line to line voltage will be 114.44. So for general corona, so simply instead of 0.7 we have to multiply by 0.8. It comes out to be 130.78. This is the critical visual disruptive voltage. Finally, let us try to find out the critical disruptive voltage and corona loss. Determine the critical disruptive voltage in corona loss for a three-phase line operating at 110 kV, which has a conductor diameter of 101.25 centimeter arranged in 3.0405 meter delta in delta. Assume air density factor 1.07 and dielectric strength of the air 21 kilovolt per centimeter. So this is actually uh, given in terms of RMS values. So disruptive voltage is given at 21 m delta r ln of d by r, because this 21 is given in the question. So m is, since m is not given, we can take it as 1. So air density correction factor is given to be 1.07. So r is the half of this, that is 0.625 centimeters. Ln of this, that is 305 converted into centimeter divided by 0.625. So it comes to be 87 kilovolt. When you multiply this by √3, it comes out to 150.6 kilovolt. But the operating voltage is 110 kilovolt, which is very less as compared to this. That means corona will not occur and corona loss will be 0. This very important point. That's why I have shown this problem to you. And the last one, a single phase overhead line has two conductors of diameter 1 centimeter with a spacing of 1 meter between the centers. If the dielectric strength of the air is this, determine the line voltage for which the corona will commence on the line. It's actually the same question, but the only thing is you can see uh, the nomenclature different. Here you are asked to find out the voltage for which the corona will take place. That means the critical disruptive voltage. So the critical disruptive voltage for phase will be 21 delta r ln of d by r. Given the value, it comes out to be 55.6 kV. But it is, I think it is still it is not complete, because it has asked the line voltage. We have to multiply √3 to this to get the actual value. I hope you understood this. Thank you.